Introductory Chemistry, Chapter 8, Quantities in Chemical Reactions. So chemical reactions are just like recipes. So for example, if you wanted to make 5 pancakes, a recipe you might follow would be that you need 1 cup of flour, 2 eggs, and 1/2 teaspoon of baking powder. So what does this recipe tell us? If I mix all of these things together, I can get 5 pancakes. Now, we keep in mind that flour and eggs and baking powder look nothing like pancakes, and they look nothing like each other per se. However, once they undergo a reaction, they form pancakes. So if I wanted to make 20 pancakes because I was having a breakfast party, how many eggs would I need? Well, my recipe says for every 2 eggs, I get 5 pancakes. Well, if I want 4 times the amount of pancakes, that means I need 4 times the amount of eggs. It also means that I need 4 times the amount of all of my other ingredients. So if 1 cup of flour gives me 5 pancakes, then that means I would need 4 cups of flour for my 20 pancakes. It also tells me that I would need 4 times 1/2 of a teaspoon of baking powder, which says I would need a total of 2 teaspoons of baking powder to make my 20 pancakes. Well, what if instead of having a breakfast party, I only wanted to make enough pancakes for myself? And let's say that was 2.5 pancakes. Well, if I compare that to my recipe, I'm only making half of the amount. So that means I would go through and I would only need half of the ingredients. So 1/2 cup of flour, 1 egg, and 1/4 teaspoon of baking powder gives me 2.5 pancakes. So chemical reactions are just like recipes, but instead of looking at individual baking ingredients, now we're looking at individual compounds. So here's a reaction to make ammonia, which is commonly found in glass cleaner. 3 moles of ammonia 3 moles of hydrogen plus 1 mole of nitrogen will give us 2 moles of ammonia. Just like with our pancake recipe, hydrogen gas and nitrogen gas are completely different from ammonia, but when we mix these things together, we can form something new. So how many moles of ammonia could be produced with 12 moles of hydrogen? I look at my recipe, which comes from my number of moles. So it says 3 moles of hydrogen gives me 2 moles of ammonia. Well, if I have 12 moles of hydrogen, that means that I have 4 times the amount that is necessary in my chemical equation or my recipe. So if I have 4 times the amount of hydrogen, that means that I can get 4 times the amount of ammonia. And 4 times 2 is 8. So that says I can get 8 moles of ammonia if I react 12 moles of hydrogen. Well, if I'm going to react all 12 moles of hydrogen, then how many moles of nitrogen would I need? Well, once again, because I have 4 times the amount of hydrogen, I need 4 times the amount of nitrogen. And 4 times 1 is 4. So 12 moles of 12 moles of hydrogen react with 4 moles of nitrogen to produce 8 moles of ammonia. I simply looked through and just multiplied my respective coefficients times 4, comparing them to my initial number of moles of hydrogen. So our general principles involving calculations are that we absolutely have to know our correct chemical formulas for all of our reactants and products. So that means if we have an ionic compound, we have to make sure that we have the correct subscripts by looking at balancing out the charges through the crisscross method. And if we're looking at a molecular compound, that we have written out the correct subscripts by looking at the prefixes for the name of our compound. Once we know all of that, we have to go in and make sure that we have a balanced chemical equation by including the appropriate coefficients, because we have to observe the law of conservation of mass. Now, our calculations are actually performed in terms of moles. Moles, remember, is a counting number. So you can have 1 mole of beryllium and 1 mole of xenon. They weigh different amounts, but you have the same number of atoms present. So that is why our reactions are based on numbers of moles and not in terms of masses. But we can do some conversions to go from mass to mass. And the fancy terminology for this in chemistry is called stoichiometry, which the base or Latin name for stoichiometry means numbers or counting. So we can look at the chemical equation, which represents the combustion reaction for water. So we can take 2 moles of hydrogen, react 1 mole of oxygen to get 2 moles of water. This is what the coefficients tell us for this particular balanced equation. Those are called the stoichiometric coefficients. So we need to have those molar relationships or ratios to each other to produce our compound that we're interested in. So what if 4 moles of hydrogen reacts with excess of oxygen? Well, what if 4 grams of hydrogen reacted with an excess of oxygen? How can we perform these calculations? So we're going to look at setting up a series of conversion factors. As I like to say, we're going to do our picket fence. And the first step that you will take is converting mass to mole. And to do that, you have to know what the molar mass is. You simply look at the periodic table, add up all those masses of the elements that are present, and the units are grams per mole. You will always start with 1 mole in that conversion factor. Then we go moles to moles, moles of what we're given into moles of what we want. Those numbers come from our balanced equation by looking at our coefficients. You have to refer back to your recipe for your chemical reaction to do this step. Then you are going to convert the moles of what we wanted into the mass of what we want. And in order to that, once again, you need to have your molar mass. So you look at your periodic table, you add up all those masses, and once again, your units are grams per mole. So this is per 1 mole because you're looking at just how much does 1 mole of this substance weigh. So you will always start this 3-step process with 1 mole on the top, and you will always end the 3-step process with 1 mole on the bottom. The only time your number of moles can ever be different is in that second step because those numbers come from your balanced equation. So your mass-to-mass conversion is simply taking these 3 steps and putting them together. This allows us to either calculate how many grams of a substance do we need to react, or how many grams of a substance can we produce. So some actual practice here. Urea, which is NH2 parentheses 2CO, is a byproduct of protein metabolism and is formed in the liver, then filtered from the blood and excreted by the kidneys. Urea can be synthesized in the lab according to the following equation. 2 moles of ammonia will react with 1 mole of carbon dioxide to produce 1 mole of urea and 1 mole of water. So how many moles of ammonia will react with 5.0 moles of carbon dioxide? Well, I start with my given information of 5.0 moles of CO2. I then look at my balanced equation and see that I have 1 mole of CO2 will react with every 2 moles of ammonia that I have. So in order to cancel that out, I have to put my 1 mole of CO2 on the bottom and my 2 moles of NH3 on the top. 5 times 2 is 10. 1 times 1 is 1. 10 divided by 1 is 10. So I have 10 moles of ammonia that are needed to react with 5 moles of carbon dioxide. So in this particular reaction then, how many moles of urea will be produced? I start with my given information again, which says 5 moles CO2. I look at my balanced equation. Every 1 mole of CO2 that I react, I get 1 mole of urea produced. So 5 times 1 is 5. 1 times 1 is 1. 5 divided by 1 is 5, which says then that I will get 5 moles of urea for every 5 moles of CO2 that are reacted. And we keep in mind when we're doing these conversions that whatever unit we start with up at the top, the unit to cancel out has to be what I like to say next door downstairs so that those units are canceled out and we're only left with the unit that we're interested in. So now taking a look at the 3-step process. So nitrous oxide, which is more commonly known as laughing gas, N2O, or dinitrogen monoxide, is used as an anesthetic in dentistry. It is formed through a decomposition reaction of ammonium nitrate. So the reaction says ammonium nitrate, when treated with heat, which is what this triangle means, will produce nitrous oxide, 1 mole, and 2 moles of water. So how many grams of nitrous oxide can be produced from 175 grams of ammonium nitrate? So there are 2 different molar masses that have to be calculated. One of our given thing that we're interested in, and the other of the thing that we want to find. So we have our given information and we have the information that we want to find. So the molar mass of ammonium nitrate, I look at the periodic table, 1 nitrogen plus 4 hydrogens plus another nitrogen plus 3 oxygens gives me a molar mass of 80.06. My nitrous oxide is 2 times the mass of nitrogen plus 1 oxygen, and that is 44.02. So my first step here is going from mass to moles. So I put my molar mass on the bottom, and I have that 1 mole on top that I said we'll always start with. Then I look at my balanced equation and see that for every 1 mole of ammonium nitrate that reacts, I get 1 mole of nitrous oxide produced. So I have my 1-to-1 relationship here. Then the last step is to convert from moles back into mass. And I use the molar mass of nitrous oxide to do that. If I go through and look at the units that cancel are grams of ammonium nitrate, moles of ammonium nitrate, moles of nitrous oxide, which then says I am left with grams of nitrous oxide, which is what I'm looking to find. If I multiply everything together on the top, I divide by everything multiplied together on the bottom. That tells me that I'm going to get 96.2 grams of nitrous oxide if 175 grams of ammonium nitrate decompose. So then from this reaction, how many grams of water will also be produced? I start with my given information again. I also need to find my molar mass of water, which says 2 times the mass of hydrogen plus 1 times the mass of oxygen, so 18.02 grams per mole. First step is to convert mass into moles. I divide by the molar mass. The second step is to look at my balanced equation and see what are my coefficients for these particular substances. There's 1 mole of ammonium nitrate will decompose and form 2 moles of water. So that's my recipe. So I make sure I'm following my units and things are canceling out. So the last step I'm going to do is moles of water into grams of water. And that occurs by multiplying by the molar mass. So everything is canceled out. This red line is in the wrong place. That should be on the bottom. But grams of ammonium nitrate, moles of ammonium nitrate, and moles of water have canceled out to leave me with grams of water. So everything gets multiplied on the top, everything gets multiplied on the bottom, and then you divide the top number by the bottom number. That gives you 78.8 grams of water. Notice if I take 78.8 and add it to 96.2, I'm going to end up with my original mass of 175. This has to make sense because whatever mass I start with has to equal the mass that I end with. So a flowchart that we can look at to apply these steps is something that I've talked about and I'm going to keep talking about in class. What are the steps that are we going to take? What are the 3 things that we need to know for our picket fence? So we always start with the mass of a particular compound. In order to convert from mass to moles, we need the molar mass. Then we're going to convert from moles of something into moles of something else because that's our counting number. In order to do that, we need our balanced equation and those coefficients that are associated with those compounds. Then the last step we take is to go from moles of a substance into the mass of that substance. And once again, that requires the molar mass that we find from our periodic table. So we start with a molar mass, we end with a molar mass. We're dividing the molar mass to begin with, we're multiplying the molar mass when we end. We are always starting with 1 mole in that conversion. We are always ending with 1 mole in that conversion. And as stated, the only time that we have a different number of moles is when we look at our molar ratio from the balanced equation. So let's say I go to my cupboard and I have all kinds of eggs and flour and baking powder, and I want to know what's the maximum amount of pancakes I can make with what I have on hand. So let's say I have 3 cups of flour, I have 10 eggs, and I have 4 teaspoons of baking powder. Well, how many pancakes would that be? So I look back to my recipe and see that for every 1 cup of flour, I get 5 pancakes. So that means if I have 3 cups of flour, I multiply by 5, I get 15 pancakes. 10 eggs. Well, for every 2 eggs, I get 5 pancakes. I have 5 times the amount of eggs. So if I multiply 10 times 5 divided by 2, that gives me a total of 25 pancakes. If I look at my baking powder and I have 4 teaspoons of baking powder, I see that for every half a teaspoon I have, I can get 5 pancakes. So 4 times 5 is 20, divided by 1/2 gives me 40 pancakes. So I could get 15 pancakes or 25 pancakes or 40 pancakes. But really, with what I have available for my recipe, the most amount of pancakes I can make is 15. This is because my cups of flour would be considered my limiting reactant. Why is this? Well, I can look here and see if I was going to use all of my eggs, how many cups of flour would I need? Well, the recipe says for every 2 eggs, I need 1 cup of flour. 10 divided by 2 is 5, which means I'd need 5 cups of flour. I don't have 5 cups of flour. 4 teaspoons of baking powder requires 1 cup of flour. Well, the recipe says a half a teaspoon of baking powder is necessary for every 1 cup of flour. I have 8 times the amount of baking powder, which means I'd need 8 times the amount of flour. That says I'd need 8 cups of flour. I don't have that. I only have 3 cups. So basically what this tells us then with any given recipe, you go to your pantry and you say, what is the most amount of something I can make based on what I have on hand? So that is what's called a limiting reactant. So when we go back to the chemistry side of things and look at our chemical recipe, we have those stoichiometric amounts, which is looking at the balanced equation and seeing what our recipe calls for. Our limiting reagent or reactant is going to be the thing that only allows us to make the minimal amount. So we are going to use up all of our limiting reactant to produce what we can with what we have. Then we have an excess reagent or excess reactant, which would be all of the rest of the ingredients that are left over after the reaction. So for example, if we react carbon monoxide with hydrogen, we can produce methanol. The recipe or the stoichiometric amounts are 1 mole of CO for every 2 moles of hydrogen produces 1 mole of methanol. If I look over here, I see that I have, if I count things out, I have 1, 2, 3, 4, 5, 6 moles of hydrogen. I have 4 moles of my carbon monoxide. Well, after the reaction is complete, I see that I have 1 mole of carbon monoxide remaining, and I've produced 3 moles of methanol. So what does this mean? If I go back and I look at my recipe, it says if I have 4 moles of CO, I'm going to need 8 moles of hydrogen because the relationship is for every 1 mole of CO, I need 2 moles of H2. I can also look at this and see, okay, I have 1, 2, 3, 4, 5, 6 moles of hydrogen. 6 divided by 2 is 3. So if I have 6 moles of hydrogen, that means I need 3 moles of CO. Well, I have more than enough CO. I actually have 4 moles. So that would be considered my excess reactant because I have some left over. I've used all the moles of hydrogen that were available. I have none of that left over. So by reacting all of my limiting reactant, I was only able to produce then my 3 moles of methanol. This is once again looking at my stoichiometry and saying for every 1 mole of, or sorry, excuse me, for every 2 moles of hydrogen, I get 1 mole of methanol. I reacted my 6 moles. 6 divided by 2 is 3. So that is how I got my 3 moles of methanol. Some other quantities that we can take a look at are what we call theoretical yield, actual yield, and percent yield. Your theoretical yield is simply your pen and paper calculation of the maximum amount of product that you can get. So the mass-to-mass conversion that I've talked about and given examples on, that is called your theoretical yield. Your actual yield is what you measure when you've finished your reaction. So this comes from actually performing the lab. And we know that in lab, we have a tendency to spill things or not add the right amount of stuff or not dry our compounds to completion. And so our actual yield is not going to be perfect, but it's what you're going to measure in the lab. So your percent yield is a number that is going to tell you how effective or how efficient was your reaction. Our goal is to get 100% yield. If you get less than 100%, then you go back and look at how do I improve the reaction or how do I improve the lab technique. If you get over 100% yield, then something has gone really wrong because we know that we cannot create mass in a chemical reaction. So this says that you either made a byproduct or your substance wasn't completely dried when you took the mass. And the way we calculate percent yield is you take your actual yield, you divide it by your theoretical yield, and you multiply by 100%. So in the book or in the problems that we're going to do, the actual yield has to be given to you. This is not a number that you calculate. It's not a number that you guess at. It has to be provided. So some sample calculations with theoretical yield, actual yield, and percent yield. Maleic anhydride, C4H3O2, is an important industrial intermediate chemical used to make coatings and polymers. It is prepared from benzene, C6H6, according to the following reaction. So 4 moles of benzene will react with 15 moles of oxygen to produce 4 moles of maleic anhydride, 8 moles of carbon dioxide, and 6 moles of water. What is the theoretical yield of maleic anhydride if 486 grams of benzene are reacted with 597 grams of oxygen? What is the limiting reactant? So you're going to do 2 series of picket fences. One where you convert one of your reactants into the product, and then you convert your other reactant into the product, following the 3-step conversion of mass to moles, moles to moles, and then moles back to mass. So in order to do this, we need to find the molar masses of the substances that we're interested in. So we were given grams of benzene, which means we need the molar mass of benzene, 6 times the mass of carbon plus 6 times the mass of hydrogen. We also have oxygen as a reactant, which says 2 times the mass of oxygen to get our molar mass. And then our product, which is the maleic anhydride, the molar mass would be 4 times the mass of carbon plus 3 times the mass of hydrogen plus 2 times the mass of oxygen. So at this point, we have all of the molar masses that we need. Then we're going to, in the second step, look at what are our mole-to-mole relationships. So for example, with the benzene conversion, and in my first step, I've divided by the molar mass. 1 mole on the top, that's how we always begin. Then I look and see that for every 4 moles of benzene I react, I get 4 moles of maleic anhydride produced. So 4 moles of the maleic anhydride on the top, 4 moles of benzene on the bottom. The last step involves then the molar mass of maleic anhydride. So I finish my conversion with 1 mole on the bottom and the molar mass on the top. So I can see then that grams of benzene, moles of maleic anhydride have canceled out, and I'm just left with grams of maleic anhydride. There should not be a red strike through on that. If I multiply everything together on the top, divide by everything multiplied together on the bottom, that is going to give me 517 grams of maleic anhydride. I perform the same series of calculations, just some of my numbers are going to change. And that would be 597 grams of oxygen divided by the molar mass of oxygen. So I start with the 1 mole on top. I then look at the molar relationship between oxygen and maleic anhydride. This says I need 15 moles of oxygen if I want to produce 4 moles of maleic anhydride. So this is where I include those coefficients to cancel. And then in the last step, I simply once again multiply by the molar mass of maleic anhydride. Seeing that grams of oxygen cancel, moles of oxygen cancel, and moles of maleic anhydride cancel. Here's when I created this slide, I was really cancel happy and put too many red lines on here. So I'm left with grams of maleic anhydride. If I multiply everything through together on the top, I divide by everything multiplied together on the bottom, I get 413 grams of maleic anhydride. Comparing these two numbers, my smaller number is going to be the maximum amount that I can get. So it's a little counterintuitive because we think, oh, the bigger number, that must be the one that we get. No, we're looking at a limiting reactant problem. So it is always going to be the smaller number that wins. So then what was our limiting reactant in this particular problem? It was oxygen, because the oxygen, we did not have enough of that to react with all of the benzene that we wanted to. So that then says that benzene is in excess, which means that we would have some of that left over. So then if we're told that the actual yield is only 328 grams, what is the percent yield of maleic anhydride? I take my actual yield and divide it by my theoretical yield, multiply by 100%. So 328 grams divided by 413 grams times 100 is 79.4%. So this number isn't the best number, so that says that we could go back in and perhaps find a catalyst that we could add to help our reaction product yield, or maybe we accidentally spilled something. So we always are trying to improve our percent yields to the best that we can. Switching gears a little bit, there's always going to be some amount of energy change that's associated with a particular reaction. When we first started talking about these in a previous chapter, when we were talking about an exothermic versus an endothermic reaction. So absolute values for energy can never be measured, only the change in energy. So we can look at where a system starts and where a system ends. And by system, we are talking about what we are interested in. So a particular reaction, and your surroundings then are everything else. So in our first box here, we see that heat is leaving the system and going into the surroundings. That tells us that this reaction is exothermic. In box B, we see that heat is coming from the surroundings and going into the system. So that tells us that this is endothermic. And our fancy way to talk about these heat transfers is a term called enthalpy. And enthalpy is when heat is transferred under constant pressure. And the symbol for our change in enthalpy is delta H. This little symbol at the top here, we would say delta H naught. And what that means is that we're under standard state conditions, which is 25 degrees Celsius and 1 atmosphere of pressure. Our units for enthalpy are going to be kilojoules per mole. So then we can look at what is an enthalpy for reaction. So now we've just clarified our enthalpy change a little more by using the abbreviation RXN as a subscript and saying delta H naught reaction. So this is for the enthalpy associated for any given chemical reaction. So when the enthalpy change is negative, we know that that would be an exothermic reaction because the energy is exiting the system. When the enthalpy change is positive, that means that it is coming into the system. The energy is coming in, so it's endothermic. So what are some calculations that we can look at for thermochemical equations? So if we just take a look at water melting, how do I know that this is water melting? Because I'm starting with water as a solid and I'm ending with it as a liquid. So this is saying this ice is melting. This energy associated is positive because in order for ice to melt, we have to have some heat. Energy has to be absorbed. Well, what if I went the opposite way and I was trying to freeze my water? Well, then the amount of energy that has to be released is the same amount of energy that would have to be absorbed. It's just the reverse process. So one energy is positive, the other energy is negative. What happens if instead of 1 mole, we wanted 2 moles? Well, then we can just multiply our energy associated with the reaction by our coefficient, by whatever number of moles we have to see, well, then that's how much energy we would need. If I have double the amount of water, I clearly would need double the amount of energy. So once again, there are going to be different energy changes that are associated with changes of state. So a solid to a liquid would require 6.01 kilojoules per mole, but going from water as a liquid to water as a gas, it requires 44.0 kilojoules per mole. So there's a lot more energy required to evaporate water or to boil it as opposed to melting it. So what are the calculations that we can do with enthalpy? So given the thermochemical equation of photosynthesis below, calculate the amount of solar energy required to produce 95.0 grams of sugar, glucose, C6H12O6. So the reaction is that 6 moles of water will react with 6 moles of carbon dioxide to produce 1 mole of sugar and 6 moles of oxygen. The enthalpy associated with this reaction is 2,803 kilojoules per mole. So if I want to make 95 grams of glucose, how much energy do I need from the sun? Well, I'm going to do a set of conversions. And this always starts by looking at converting mass to moles. So that means I need the molar mass. I find the molar mass of glucose by taking the mass of 6 times carbon plus 12 times hydrogen plus 6 times oxygen. That gives us 180.1 grams. So my first step then, I start with 1 mole on the top and the molar mass on the bottom. Then I see that for every 1 mole of the reaction that I do, I'm going to get 2,803 kilojoules. So I'm canceling out then my moles of sugar. So grams of glucose cancel, moles of glucose cancel, and then I'm left with my units of energy. So multiplying everything together on the top, dividing by everything multiplied together on the bottom tells me that I am only needing 1,480 kilojoules per mole. So notice I have less than 1 mole of energy associated with this because I have less than 1 mole of my mass, of my molar mass that's associated with this, right? This is almost half of the molar mass, so I end up with about half of the energy that I would need. Charcoal is primarily carbon. Determine the mass of carbon dioxide produced by burning enough charcoal to generate 9.00 times 10 to the second kilojoules of heat. So now I'm going to start with energy and I'm going to end with mass. Notice that my delta H of this reaction is negative. This tells me that the reaction is exothermic or the energy is exiting the system. So I start with my given information, which is energy. I then look to see what is my relationship for every 1 mole of carbon dioxide that I produce, I get 393.5 kilojoules released. So this is my first setup for my conversion. Then I once again need to know the molar mass of the substance that I'm interested in. So I look to the periodic table and I calculate 1C plus 2 O's gives me 44.01 grams. So I multiply by the molar mass, and that's going to give me my initial amount, or sorry, my final amount of carbon dioxide that can be produced. So by multiplying everything together on the top and dividing everything multiplied together on the bottom, I end up with 101 grams of carbon dioxide.